Welcome back to chemistry. Let me blow up the slide for this achieve problem. So there are two parts to the problem. The first part is calculate the maximum wavelength, lambda max, of electromagnetic radiation that can eject electrons from the surface of gold, which has a work function, symbolized by the Greek letter phi, of 8.76 times 10 to the negative 19 joules. And they want the answer in meters. But then there's a second part, which is more difficult. It says, if the maximum speed of the emitted photoelectrons is 4.05 times 10 to the 6 meters per second, what wavelength of electromagnetic radiation struck the surface and caused the ejection of the photoelectrons? And they want the answer in meters. Okay, so if you can reduce the slide. Okay, so the first part isn't so bad. And so what you essentially have to do is you have to figure out what the wavelength of light needs to be such that it provides photons with the energy that matches the binding energy of the electrons. Now, one thing I want you to note is that the binding energy of the electrons, which is the work function, notice it's in joules. So that's good. We don't have to worry about converting things from, say, joules to mole into joules. So that's good. So what we first want to do is let's just write down what this binding energy of the electron is. So this is the binding energy of the electron. And so this is the same thing as the work function. I call it binding energy of electrons. Some books will call that. Other books would call it a work function. And so we're given a value in joules, which is nice. It's 8.76 times 10 to the negative 19 joules. So what you have to do is to figure out what is the wavelength of the photons necessary to provide an energy that beats the binding energy. So here, the work function, or the binding energy of the electrons, must meet the energy of the photon. So it must meet the energy of the photon. So I think what you can see now is that the energy of the photon is going to be 8.76 times 10 to the negative 19 joules. Okay, so from this, it's not so bad to figure out what the wavelength of the photon is in meters. And so let me show you how you go about doing that. So you might recall that energy of the photon is equal to be h times the frequency of the photon. But if you wanted to, you can substitute into frequency of the photon c over lambda. So I'm going to do that. So the energy of the photon is going to be equal to h and then c over lambda of the photon. And so what I'm going to do now is I'm going to solve this equation for the lambda, or wavelength of the photon. So the wavelength of the photon, lambda of the photon, is going to be equal to h times c over the energy of the photon. Okay, and so at this point, you can go ahead and plug in numbers. So let me just do that really fast. Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. And then we have speed. I'm going to use achieves. Speed of light, which is 2.998 times 10 to the 8 meters per second. And then what I'm going to do is divide that by the energy of the photon. And so that is here, it's 8.76 times 10 to the negative 19 joules. Okay, so when you work this out, what I got, and I'm just going to go ahead and round this to correct number significant figures, I got 2.27 times 10 to the negative 7 meters. Okay. So now what I want to do is I want to move on to part 2. So let me erase the board. Okay, so let's look at the second problem. I'm just going to read it out loud really quick. If the maximum speed of the emitted photoelectrons is 4.05 times 10 to the 6 meters per second, what wavelength of electromagnetic radiation struck the surface and caused the ejection of the photoelectrons? Okay, this is a very difficult problem in my opinion. Okay, so here's the deal. What they're wanting to know is if you know what the velocity of one of these electrons flying off is, and you know what the binding energy of the work function of the gold here you're dealing with is, can you work back and figure out what the wavelength necessary of the light striking the gold atoms was to get this electron flying off at that speed. So let me just kind of remind you of a basic principle. It's this. When you have waves of light that are beyond the threshold frequency or the work function or the binding energy of the atoms here in the metal, some of that energy is used to meet the binding energy, but all the rest goes into the kinetic energy. So the total amount of energy that this metal is being hit with should be equal to the binding energy of the electrons to the metal plus the kinetic energy which the electrons are moving off with. So one formula you can generally use, which is helpful, is that the total energy of the light is going to be equal to the binding energy of the electron. Get a better pen here. So this is also known as the work function. So I'm going to use phi there. And then it's plus the kinetic energy. Okay, so let's kind of break this down a little bit further. And so one way we can sort of think about the total energy of the light is you might remember that the energy of the light is equal to Planck's constant times frequency of the light. Now here we're actually dealing with individual photons striking the metal and getting individual electrons released. So we can say that energy of the photon is equal to h frequency of the photon. And then from here you can work out that energy of the photon is equal to h c over lambda of the photon. So what I want to do is substitute the energy of the photon into the total energy of the light. So here I'm just going to write, instead of total energy of light, I'm going to write hc over lambda of the photon is equal to the binding energy of the electron plus the kinetic energy of the electron. So here's the deal. We are given the velocity of the electron, and from that you can work out the kinetic energy. I'm going to show you how to do that in a minute. We are given the binding energy of the electron. You know Planck's constant, you know what the speed of light is, and so you can solve for the wavelength of this photoelectron. So I should say, when they're talking about photoelectron, that's the electron flying off the metal. A photoelectron is just an electron that's been released from the metal by light. Okay, so let's go ahead and solve this. So the first thing I want to do is, I told you that if you know the velocity of the electron that's flying off, you can work out the kinetic energy. That's a bit of a pain. So let's go ahead and do that now. Let's get that out of the way because this is not a lot of fun. So yeah, the kinetic energy of the electron is going to be 1/2 the mass of the electron times the velocity of the electron squared. So what you're going to have to do is you're going to have to plug in the mass of the electron and then the speed of the electron, which is given to you, and you're going to have to square the speed, divide that by 2, and that gives you the kinetic energy of the electron. So let me show you how you do that. So it's going to be 1/2. And so one thing you may be wondering is, do I need to use the mass of an electron? The answer is yes. Another thing you may be wondering is, do I need to use the mass of the electron in grams or kilograms? You have to use it in kilograms. And the reason is, when mass is in kilograms and velocity is in meters per second, when you square velocity, that'll be meters squared over seconds squared. Then you'll have kilograms meters squared over seconds squared. And so one of the things you might remember from 109 is that 1 joule is equal to 1 kilogram meters squared over seconds squared. So if you use a kilogram mass, when you multiply by the velocity squared, you will get an answer in joules, which is great. It makes our lives a lot easier. So we want the mass of the electron. And so the mass of the electron is, you'll have to look that up, but I'll show you what number I got here. So it's 9.109383 times 10 to the negative 31 kilograms. And then you're given the speed of the electron, which is 4.05 times 10 to the 6 meters per second. You're going to have to square that. Okay, So you really have to do the math carefully. You first have to square the speed here, and then multiply by the mass of the electron in kilograms, and then divide by 2. And so when I did that, I got 7.47083 times 10 to the negative 18 joules. Okay, so this is the kinetic energy of the electron. And so now the problem gets a little bit easier to solve. And so you might remember here that Planck's constant times the speed over the wavelength of the photon is going to be equal to the binding energy of the electron plus the kinetic energy of the electron. So the binding energy of the electron is given to you in part 1. So let me write that in. It's going to be 8.76 times 10 to the negative 19 joules. The kinetic energy of the electron is that value there, 7.47083 times 10 to the negative 18 joules. And when you add these numbers up like you have to do, what I got was 8.3468. That's probably enough significant figures. Times 10 to the negative 19 joules. Okay. Now, we'll just round that just to make sure. I think you can see if this is an addition. This is probably going to have to be rounded to 8.35 times 10 to the negative 19 joules. Okay, and so that is the energy of a photon. So the final step isn't so bad, so I'll do this work over here, in that you probably know that the energy of the photon is equal to h times the speed of light over the wavelength of the photon. So you need to solve this for wavelength. The wavelength of the photon is equal to hc over the energy of the photon. This is really good on my back. Okay, so h is 6.626 times 10 to the negative 34 joule seconds. We will use the achieved speed of light, which is 2.998 times 10 to the 8 meters per second. Divided by the energy of the photon. The energy of the photon is 8.35 times 10 to the negative 19 joules. And so when I did this earlier, rounded to correct sig figs, I got 2.38 times 10 to the negative 8 meters. Okay. Thank you for listening. We'll see you next time.